Hi, everyone, and happy National Chemistry Week. I'm David Horwitz, a program manager in the American Chemical Society's Office of Science Outreach, and I want to thank you for being here today for this inspiring discussion about the importance of adhesives. As you know, we're sticking with chemistry this week and learning all about glues and adhesives. Since National Chemistry Week is a public awareness campaign, it's our mission to tell the world how important chemistry really is. So make sure to talk about the importance of chemistry on social media and with your friends and family this week and all year long. Before we get started, let's talk about the format of today's webinar. First, I'll pass it off to our moderator, who will introduce our three esteemed experts. Second, we'll hear about each panelist and learn how they got into the field. Third, we'll learn about the importance of adhesive science and where the field is headed. And fourth, we'll open up to questions from you, our audience. We'll save all of your questions for after the discussion. And if you have any questions for our panelists, please type them into the questions panel for our moderator, and we'll make sure to ask them during the live Q&A. So without further ado, I'd like to introduce my colleague, Dr. Lily Rains, who will moderate today's panel. Lily is the manager of the ACS Office of Science Outreach and has been since 2017. She oversees our efforts to provide programs, training, and resources to ACS volunteers interested in conducting community outreach. She manages a portfolio of landmark programs like this one, National Chemistry Week, as well as others like Chemists Celebrate Earth Week, the US National Chemistry Olympiad, International Chemistry Festivals, and more. Lily earned her doctorate degree in biochemistry, cellular, and molecular biology from the Johns Hopkins University School of Medicine. Please help me welcome Dr. Lily Rains.
All right, well, so I'm Lily Rains. I manage the ACS Office of Science Outreach. We oversee a variety of programs that are all targeted towards helping chemists be the best outreachers they can be. And now I'm going to introduce our panelists. Our first panelist is Dr. Alejandra Alvarez Albaran, who is a hardware research engineer at Facebook Reality Labs. Alejandra holds a PhD in polymer science from the University of Akron. Since completing her doctoral program, she has worked for various industry leaders, including DuPont, PPG, Zymergen, Tesla, and is now at Facebook. Alejandra has broad experience in the adhesives field, including leading cross-functional teams for the development of new materials and applications in different industries. Alejandra, can you tell us a little bit about how you got into adhesion science?
Sure, thank you, Lily, for the nice introduction, and thank you for the invitation to the panel. Well, yeah, initially, ever since my undergrad, I was in love with polymers, so I knew that I wanted to pursue a career in polymers, right? And then after that, I think my first exposure to the adhesion of science was during my PhD, where I developed a specific coating to improve the biocompatibility of breast implants. So for that part, it was very important that the coating would stick to the surface of the implant. So that's when I first started to understand what adhesion meant in the polymer field. Later on, in the first opportunity I had after my PhD, I led a research group at PPG, where we basically developed new adhesives for the field, mostly for automotive industry. But then we had a lot of cross-functionality in our team. So then I realized that adhesives are not only for automotive objects, but it's also like everywhere where we touch, right? So it's adhesives for aerospace, for like marine industry, etc. Even when you get to the dentist, you are in contact with adhesives, right? So adhesives are everywhere, and that's why I love working in this field.
Great, thank you so much. Our second panelist is Dr. Anne Fornoff, who is a senior research specialist at 3M. Anne works with diverse teams of scientists and engineers to develop new technologies to make innovative products in 3M's Electrical Markets division. Since joining 3M, her work has led to 24 issued patents, recognition with the highest level peer-nominated award at the company, as well as recently receiving the American Institute of Chemical Engineers Rising Star Award. Anne has also chaired 3M's Tech Forum, where she was responsible for connecting 3M's technical community and served as a 3M ambassador at external events to showcase the technical community's achievements. Anne regularly speaks to groups about STEM, works with startups through the 3M supported accelerator program, and mentors aspiring engineers and scientists. Anne, can you tell us about how you got into adhesion science?
Absolutely, and thank you for that nice introduction and also for including me on the panel. I'm excited to talk about adhesives today. So much like Alejandra, my introduction was really through polymer science. So I studied polymers at every length scale. So when I was in grad school, I looked at the bulk. When I did my first postdoc, I looked at nanometer scale interactions, and then polymers on the single molecule scale. So I did something called electric glue when I was in Hermann Gaub's group, and this was really fun and really looking at, fundamentally the interaction of a polymer with a surface. So that's really where I got introduced to adhesion science, and then moving to 3M, where I work now, that's a lot of what we do. So for me, what's important, I think, as I understand it, we've got a lot of young people who are joining the call. I think it's really important you see us, and we're, mid-career, late career, and we didn't just magically get here. I certainly had a lot of help throughout the way, a lot of mentors, and I think all the panelists would say that they've had great mentors that help bring them into the field and then also help them along the way. So if you're a student, don't be intimidated when you hear like so many patents and already working in this field or this career path. You really do end up with a lot of help. So for that, I'm grateful, and I love adhesion science.
Great, thank you so much. Our third panelist today is Dr. Charles Paul, who goes by Chuck and currently serves as the Vice President of Technology at Henkel Adhesive Technologies. Chuck has a PhD in chemical engineering from UC Berkeley and over 30 years of experience in materials research and development and R&D management. His expertise is in polymer-based systems, where he has published several book chapters and holds over 60 US patents. In his current role within new business development, Chuck provides technology assessments for all potential investments for mergers and acquisitions or new ventures. Chuck, can you tell us how you got into adhesion science?
Yes, I think when you talked about the late career panelists, you're referring to me. So, so yeah, like both Anne and Alejandra, it started with polymers, and I did work in polymers for a couple of big companies. I did a postdoc at IBM. I did worked at DuPont and also Allied Chemical, and there wasn't quite the level of mystery to some of the problems that you tried to solve in the big chemical companies. They're kind of more very long term, pretty well known, where you had to get to, and the problems were more tractable, I would say. But I tended to actually I found this out when I did recruit, and I was recruited for a job that he said. I told him what I like to do. He said, "You'd like to do product development." So, and in the adhesion world, product development, there's a lot of opportunities because there's all different substrates, all different processes, never mind all different adhesives, right? And applications. So you get a lot of chances to do that. And that's how from polymers to a job, I kind of drifted into product development and ended up at an adhesion company and stayed here for 32 years. So it's been great, and I love it, and I go to a lot of the adhesion science conferences still because I'm trying to get insights as to how to make better adhesives.
Great.
It's a fun job.
Well, thanks again to everybody for being here today. Let's start with a basic understanding of adhesion science. Panelists, how would you define adhesion science, including what is so important about the field and what are some important applications of adhesion? Anyone can go first.
Ladies first.
Well, sure. I think that like a very simple definition of adhesion science is the tendency to bond dissimilar substrates or like surfaces that are not similar to each other, right? And that's one of the biggest challenges that we have in the adhesion industry, because most of the times when we're trying to make a new product, we end up wanting to bond dissimilar substrates. By dissimilar substrates, I mean that there's our substrates that have very different chemistries between them, right? So for example, if we want to bond like, I don't know, a silicone to a glass or like a silicone to like an aluminum, you are working with two very different chemistries. And that's one of the biggest challenges that we have in the adhesives industry, really, right? Like to make these adhesives strong enough and robust enough to bond dissimilar substrates that have nothing in common in terms of their own chemistries. In addition to that, I think another challenge that we have in the adhesives world is the robustness, is to ensure that the adhesive is going to be robust enough to like last for long periods of time. And this is when like the applications come like very important, right? Like the applications of adhesives are in, like I mentioned before, in the automotive industry, but also like in the marine industry, where the adhesives are exposed to like very corrosive environments with high levels of humidity, different temperature cycles. So we need to develop adhesives that actually survive these type of environments, right? If we're working for like, I don't know, like designing adhesives that will be like in the exterior of a home, you have to make sure that the adhesive is going to resist like the thermal changes, right? If you live in Pennsylvania, you will have a very warm summer with like a lot of humidity, but also in the winter, you will have very low temperatures, exposed to snow, etc. So that's the importance of like developing robust adhesives, and like because their applications are like everywhere, like the fields of applications of adhesives is like very, very broad, even including in the medical field, where like the exposure of the adhesives, they need to survive in a very aqueous environment, a different like at our body temperature, right? So they're exposed to very different environments, and that I think that's part of the importance of the application, that they're like everywhere, and they need to be robust enough to basically keep all the layers together.
I think Alejandra hit on the, obviously the critical aspects of adhesives. And, I just note that, we kind of think of ourselves in almost two camps also in adhesion science. So there are pressure sensitive adhesives, and these are ones that you would find in like your tape or Post-it notes. They're tacky and removable. Right. So in those instances, you don't want your adhesive to stay there for 30 years, right? The whole point of a Post-it note is you can take it down and not have it be permanent. But then on the other side of things, there are structural adhesives. And these are the kinds of bonds that you do want to last for 30 plus years and very strong. And we should really care about them, because these are the kinds of adhesives that bond airplane wings to the body of the airplane. So, and then also, there are a lot of automotive applications like Alejandra brought up. On the PSA side, in your cell phone, in your computer, in your TV. So everybody is probably a foot or two away from PSAs right now, and they enable those technologies. So definitely an exciting field.
3M was going to bring up the Post-it note at some point. It had to happen.
Yeah, it's a great restraint to not talk about command strips, but
that's another really good invention. On the adhesion science side, so we talked a lot about product development applications. On the adhesion science side, if you talk to some of the leading professors, they'll say, you know what, you guys developed the adhesive that works, and then we try to figure out why it worked. And that is actually often what happens, that they really spend a lot of time teasing out the mechanisms, not just how our adhesives work, but geez, how does that bug stick to that? Why does a fly stick on the ceiling? Exactly how does that work? And that's not an easy problem. So they're able to tease out those things and give us insights, and we can go back to the lab then and make better adhesives, hopefully. mean, some of them also participate in trying to make better adhesives. But I would put adhesives even broader than was already mentioned, in the sense that coatings are also adhesives, right? They have to stick to the surface. So again, as the oldest panelist, I remember cars, they all started to rust at 7 years old. Forget it, they started to rust. That doesn't happen now. That doesn't happen now because of adhesives. And adhesive scientists have then helped to figure out exactly the mechanisms by which that's true. It's largely impact resistance. I'll mention Tony Kinloch, one of the founders of the Adhesion Society, who studied that problem and really led to the great understanding of exactly how that works. And then there's other areas that we don't think about, like food packaging, right? So those potato chips you just ate had several layers to keep them fresh, right? And those were stuck together with adhesives. It may sound trivial, but I mean, food packaging preserves food much longer than it used to be preserved. So it really reduces waste dramatically, besides being convenient. And on the sealing side, you think of the standard things like cars and your house, your tub, right? Caulks and sealants. But there's also more advanced things like fuel cells, which require very special sealants. Or if you have a fancy phone, which I don't get to have from my work, but a fancy phone with an OLED display, that has to be sealed, because that's dead as soon as water and oxygen gets in there. That's just a few other ones. There's many. I didn't mention thread lockers yet. I'm getting there. That's
Great, great. Well, that brings us to our next question. What is the field doing and working towards to make adhesives more green and sustainable?
So that's a great question, and it's one that I think we all care a great deal about. And again, there are really distinct ways to think about this, from raw materials. So it's almost like going back to the future. The first PSAs were made from natural products, and I mentioned the sticky, tacky type adhesives. And when you remove them, you want them, all of it, to come with that substrate, right? You don't want to leave behind the gooey mess. And so the historical raw materials that came from renewable resources need better functionality. And so there's a lot of work that's being put into that. In our own manufacturing of how we make adhesives, I think, Chuck, you've done quite a bit of work, I believe, looking at solvent-free processing, which is really important to us, as well as, can you reduce the waste as you're making the adhesive? So certainly there. And then finally, in my mind, this is how I think of it, at least, in these buckets, around recyclability, and how can we build into these systems that, as Alejandra was mentioning, should last us 30 years in their application, holding the airplane wing on. You want it to really stay there, but when you want it to come apart, you want it to be recyclable and to be able to trigger that. So there's a lot of really exciting chemistry that goes into each piece for green and sustainability of adhesives.
Yeah. So the recyclability, I would just point out something that, the Amazon mailer is something that people are familiar with, right? That has the paper on the outside, and then it has bubble wrap on the inside. And so Henkel has worked and launched last year a foamable adhesive, which provides the cushioning without any plastic film on the inside. So now you can take the whole pack and recycle it. So there's a lot of work in that, in the paper area of, we have all these other things to make paper products better, but now they're harder to recycle. So how can you fix that? And so this is one example, but there are other examples where people are looking at adhesives that promote recycling. I mean, on the PSA side, the post office did a lot of work 20 years ago trying to study how do you make, they wanted to switch from gum labels to pressure sensitive labels. They did, right? And then they're like, oh, now this problem is now you got to recycle this paper, and I've got all these sticky PSA stuffs that 3M makes and Henkel too. And so how do you solve this problem? And the answer was actually to make the adhesive a little bit stronger and not make it break up in the water, but actually make it stronger so it was easier to separate. So, and that's, you know, there's issues around bottle labels, there's issues around recycling, you know, plastics. There's all kinds of issues that that adhesive people can help to solve. So we've invested actually, I think it was beginning of this year, early last year, in a recycling company in Europe that can take these flexible packaging, which has got usually a layer of polyethylene, a layer of aluminum, and a layer of PET. And in Europe, you're going to have to be able to recycle everything back to the pure components. So we're working with that company to provide adhesives for those layers that are suitable, amenable to this recycling process. So again, it's, you know, problems are good for us. It gives us jobs and things to do.
I would like to add, like Anne mentioned, there are like many different parts of the supply chain that get hit by these. In terms of the raw materials, there are biotech companies actually working on developing more sustainable monomers that will help us create more sustainable polymers, right? Like for the longest time, like we have been relying on like traditional chemistry to synthesize our monomers and come up with different polymers. Right now, biotech companies such as Zymergen, for example, they're working on basically modifying and revolutionize this field by many times modifying or synthesizing molecules from microbes that will be much more sustainable than like the traditional chemical ways. And also being inspired by what we see in nature, right? For example, mussels, they stick very well to different rocks and themselves in a very corrosive and like very challenging environment. So also trying to learn from nature to develop our new adhesive that will be much more sustainable for our world.
Great.
So Zymergen is a good example. I think, Lily, you're a biochemist, right?
Mm-hmm.
So yeah, Zymergen is a pretty cool example. And they're not only making them, you saw CNN News 2 weeks ago, right? What was the headline, right? Milk without the cow. Well, they're making proteins, right? With custom designed proteins. We still use casein from milk for bottle labeling, right? So the idea of making specialized proteins for adhesive applications is a lot of opportunity there, I think. So I think that's, Alejandra, that's a really fruitful area. I know Zymergen has come out with a polyimide film based on, which is, I don't know how they do that, but that's pretty interesting.
Yeah, I actually worked on it for a little bit.
Oh, okay.
I've got one last question.
I could give you some other examples of
Sure.
and people can build on some of these other things. So, I mean, things we don't think about as sustainable, but, you know, we have a cementitious products business. You know, cement uses 7% of the world's energy. I think that's the number every year, right? To basically take calcium limestone and convert it to calcium oxide by burning off the CO2. Lots of people are working on low CO2 cement by using aluminosilicates, by using calcium sulfates. So there's a lot of effort there to make cement more sustainable. We are also talking with companies. There's a company in Costa Rica that takes waste plastic, any waste plastic, any waste. It extrudes it with some, well, I won't give all the details away, but some other stuff, that you end up with these little crumbs that are now lightweight crumbs, and they replace sand in cement. So now you have a concrete block, which is lighter, a little bit of noise dampening, right? A little bit of vibration dampening, and a little bit of thermal insulation. And you've locked up this waste forever. And actually, you can regrind that block and put it into a road somewhere, and it's a tougher road than it would have been otherwise. So there's a lot of work you'll see in low CO2 cement. You'll also see a lot of work in right now, and I would put this in this category, is anti-infective coatings. So a number of people trying to, there's a lot of work on just the disinfectant temporary side, but there's a lot of work also on the permanent side for things like that you touch all the time, right? And also for coatings in any kind of public area that will kill bugs that happen to be deposited there. A lot of effort there. And then there's the old traditional one that we forget about because it's been going on forever, is low formaldehyde-based products, right? There's more and more stringent applications, and new technologies are coming out. So liquid PURs are replacing typical urea formaldehyde-based adhesives in wood bonding. That trend will continue. And people are looking at, again, natural products, like you mentioned, Alejandra, proteins, that they used to use, right? But now, how do you get them back in at a reasonable cost? There's a lot of effort there, and bright future.
Great. Well, we'll start taking questions from the audience. So Nicholas asks, panelists are talking a lot about polymer adhesives. Can small molecules work as adhesives too? Are they used commercially?
Anyone want to jump in on
that? So I think that, it depends on what you're thinking about in terms of adhesion and adhesives. We've talked about, some pretty specific applications and how a lot of us, actually, I guess all of us are polymer scientists. But, I think that there are ways to think about small molecules and how they bond and how you can use them to adhere things. So there's some really cool work using DNA origami, where you take one single strand of DNA and then you fold it into whatever shape you'd like. So you can make just a square, for example, pinned together with small pieces of DNA. And what's cool about, so that in and of itself is cool, but what's really cool is, people are working to then build microprocessor chips on top of that DNA origami. And so you have this really beautiful specific binding from DNA. So, Mother Nature, again, wins, right? Gives us these great tools to be able to specifically bond. And then you can put your nanomaterials on top, make your microprocessor chip, in theory, so that's still being worked out, and then burn off the DNA origami. So it's your molecular breadboard, and you can build from there. So these are small molecules. So obviously the one long strand of DNA is big, but everything else is small, and purposefully so. So we can access with traditional photolithography 100 nanometers in a length scale. What this allows is that you can get to 10 nanometer spacing, so really, really fine spacing, and you have this really beautiful specific binding from the DNA. So I think there are lots of ways to think about adhesion and how you bond to different materials. And that's one that in my mind comes up about it's very important so that you can place the materials very specifically and in that kind of length scale to have the right bonding.
Small molecules don't usually have they don't have a lot of mechanical integrity or rheology, right? I mean, rheology that's what 3M's all about, and mechanics. So that's where it's hard, but they are helpers in a lot of. So I mean, people like to use solvent-based adhesives. Why? Not just because they can deliver high molecular weight polymers, but because the solvent attacks the surface and helps the polymer get in there. People like to use acrylics on a wide variety of plastic surfaces because it's acrylic monomer, it's low molecular weight, but it gets in there and it helps the material to bite into the surface. The primers that we use often have, I mean, there's primers we have which have low molecular weight materials which initiate from actually within the surface the polymerization of the adhesive. So the only place I've seen them used actually separately as an adhesive is on applications where people are using it to hold things temporarily and using basically vacuum suction to transport things, you know. But as an aid, they're really invaluable, low molecular weight materials.
And just to follow up on what Chuck was saying, so in traditional, adhesives, I think that he alluded to this, and maybe we skipped over this when we were talking about, basics of adhesion science. But I think we would think of it as, there are surface interactions that are very important, so that Alejandra alluded to it, that the dissimilar bonding. So that chemistry at the surface is extremely important, but then also the rheology. So how do you dissipate the energy as you pull off an adhesive, gives you that adhesion strength. And so there are, certainly everyone, polymer scientists and small molecule chemists, I think we need you all for adhesive science.
All right. Melinda would like to ask, what patent or product that you helped develop are you most proud of? Alejandra, would you like to go first?
Sure. Well, I think probably I can give 2 examples. First of all, the additive development work that we did at PPG, because that was basically one of the first structural adhesives formulation that the company offered, specifically for like lightweight substrates, such as aluminum, right? For like the longest time, we've been very comfortable working with stainless steel, basically with steel for like automotive industry and many other industries. That was like very well known. However, aluminum has offered like new challenges in the field. So that's probably one of the most most important developments I've had during my career. Especially this adhesive was like impact resistance at like very low temperatures, which is very challenging to reach. So that was amazing. And probably the other part would be, I don't know, probably like the work that I did at Tesla, which was basically the development of the V3 of the Tesla solar roof. That was a project that was very fast-paced. In this way, I mean, my career at first, I was basically formulating and making new adhesives, such as like in my job at PPG. And then after that, I transitioned into what I was the customer before, right? So working at Tesla, now I'm like the customer. So now I need to qualify different, well, back then in Tesla and now in Facebook, I need to qualify different polymeric materials to make our products, right? So now I'm like on the side where I need to make sure that the adhesive is robust enough. But I also know what it takes to develop an adhesive from scratch, right? Especially if it's like a new material for new products. So then the other example that I can give when I was already working as a customer would be the development of solar roof for Tesla. It was a very fast-paced project, obviously, very strict, like very tight timeline. And well, the roof needs to survive like over 30 years, right? So the selection of all the components in that roof was also very exciting. I had to work with a lot of different suppliers and a lot of different reliability testing to make sure that the adhesive would actually survive. So I was like breaking adhesives like pretty much every day to make sure that they would survive. So yeah, those would be like my two most fun examples where I've worked so far.
Go ahead, Anne.
And
Sure. So I was thinking about this, Alejandra, as you were talking, and you had such nice reasoning. I was just going to go with the most recent. So for me, we launched in the U.S. Last, maybe, I think last week, Temflex 165 and Temflex 175. So this is general use final electrical tape. So important for electricians, and yeah, it's definitely exciting. But again, I think we've got some students on the line, and I think one thing again to say is that when you go into science, chemistry, and typically most of what you do won't necessarily be that successful experiment, right? So we do a lot of experimentation, we do a lot of work, we really pour ourselves into our projects and our jobs. And I think what's important to know is that we can point to successes, but there's a lot of not success that goes into it. And I think the important thing is that if you're if you're a student, the important thing is learn from it. Take what you from that not successful project, and then apply it to be successful in the future. So yeah. Chuck, I'm curious which ones, what products you're most proud of.
Yeah, I guess I developed I'm most proud of one of my earliest patents, which was, and again, a lot of these patents you're building off the work lots of other people have done, right? And you're taking it to a next step or another place. But we developed here diaryl substituted acetylenes, which were used as end cappers for polyimides for aerospace. And I worked really hard on it. I was really excited about it, and NASA picked it up, and Virginia Tech picked it up, and it's still flying, and it's the best. High temperature polyimide, it's still the best. And I was great because we had a meeting, and we only had a group of like 5 of us, and they're like, "How can you compete against DuPont?" I said, "DuPont gets to pick one path. They might not pick the right path. We're going to go. I think this path is better, and this is why." So you get those opportunities, and those are great. So now I do venture, and I look at other people's work. It's exciting, but it's not like when you do it yourself. When you find something yourself, it just feels fantastic. So that's my most exciting one. I've had other ones which I'm also happy for. A body side patch, which is for the Thermacare patch. If you've ever put one on your skin, that's patented. I think patents expired at this point, but that's one of the patents. So anyway, yeah, the most exciting one was one of the early ones, but it's the ones you put your most energy into. Those are the ones that get you excited.
Great. Well, a lot of people have questions about dental and medical applications, particularly thinking about making adhesives that are safe to be ingested or to enter the bloodstream. So how can you make adhesives safer? Are they already very safe? What do you look for in those kind of applications?
So we don't do those at Henkel because we're a family-controlled company. They have major share, and they said don't go in the body. No, because we don't want to get sued like others.
yeah, thanks.
So yeah, sorry. No, go ahead, Alejandra.
Well, I was just going to say that that's usually like a big concern in big companies. So that's why not all the companies want to take these type of adhesives into their portfolio, right, and development, and But I think one important thing to say is that when you're qualifying a material that goes like into the body, or that is going to be like in contact with your body, there are a lot of different regulations that the material has to pass. So if the material do not pass these formulations, these materials are not going to be in contact with your skin or your body. So there are just like, there's a lot of work that you have to do before you can actually qualify a polymer, whatever that is, even if it's like an adhesive or not, to go into contact with human beings, right? Such as, and there are different levels of qualification through the FDA, right? Depending on like how intrusive the device is going to be in the human body, right? So for example, there are like syringes that are like, you know, not closely in contact with the human body, but then you have the needle, then that might be like a different level of qualification, and then you go like into implants or prostheses, etc. So every single medical device has a different level of qualification that they have to go through, depending on how invasive they're going to be, like how invasive the device is in your body. And that's also one of the challenges why like sometimes not everybody wants to develop new materials for the medical industry, because it just takes very, very long time for them to get approved and be commercialized. So there's a lot of work in the background before that adhesive gets put into like our teeth, or like that polymer is molded into like an organ that's going to save our lives. But I think still it's a fascinating field, and we should still continue to make the effort to integrate polymers and adhesives into the medical field, because that saves lives.
Agreed. And
sorry, Anne, go ahead.
no, go ahead.
Maybe you can build on this, because there's a very active area in dental implants, because dental implants are a nightmare for people. I don't have any, thank God, not yet. But they take many steps, in like almost a year, I think. They have to use a temporary sealant, and then they have, anyway, it takes a long time. So there's a lot of work, trying to do it in one operation. And so those are adhesives that have to stick your jaw to the tooth, and then have to be resorbed by the bone over time. So there's a lot of effort in that space. I don't know, maybe 3M is involved in that as well.
Yeah, that's a good question. I don't know about the specific application, but I did work on dental fillings and some patent art around some of the chemistry in dental fillings, or you know, one subset of that 3M makes. And Alejandra is exactly right. There's a lot of regulation, and so those projects take a long period of time to go through and to make sure that what we're making is safe and effective and meets all of the regulatory standards. That's actually one that I'd say that I'm also really proud of, that area and those patents. Really cool chemistry. And you know, probably for me, the best part, you know, are the teams. And so, you know, I got to work with Joe Oxman, who is an ACS Industrial Polymer Scientist of the Year award winner, Guy Jolie, Larry Kresge, you know, all these really great folks. And so, you know, that's another part of being in adhesives and adhesion science that's fantastic, is really the teams, and that you get to work with these great people. The other thing, another area that 3M is active in is adhesives that go on your skin. And there's been some really nice work. I did not participate in this at all, so I can I can be very effusive, but I think it's really fantastic. Some really nice silicone adhesives, and they're really gentle to your skin. And so when you remove them, yeah, it's not a painful removal.
Great. Well, Kyra would like to ask a very chemistry question. What are the specific examples of the intermolecular interactions that are used in adhesives, particularly temporary adhesives?
I love that. That's great. Chuck, do you want to go first?
Well, I was just going to say van der Waals forces. That's number one. That's what the gecko uses, right? It took them a long time to figure that out. But there's plenty of others. Maybe you want to elaborate on some that, I mean, van der Waals is the weakest, right? So, you know, we try to, for example, pressure sensitives, try to cross-link the pressure sensitive. So no matter how hard it's stuck, it's not going to rip off and end up on your skin or wherever. But put enough functional groups. The most common one is just carboxylic acid group, but you can put others on, cyanate, things like that. That, you know, depends on what the surface is, right? So if the surface is PVC, like an electric tape, you know, maybe you want to put on some basic groups because PVC is acidic, right? Because the proton's next to the chlorine pulls all the electrons over there, you've got an acidic proton. You want to stick to PVC, you need a basic material. So, because you want to also stay on the backing, right? In the case of electric tape, it's the backing. So those are a couple of specific examples.
I love non-covalent interactions, so this is this is one of my faves as well. And so, you know, van der Waals forces, absolutely. And then, you know, I'm glad you gave me some meaty room for, you know, there's always two of our go-tos are hydrogen bonding and ionic interactions. And so, you know, in your non-covalent playbook, those are ones that we certainly pull out for that surface interaction.
Yeah, I was exactly going to mention hydrogen bond, because that's also like what we find in nature a lot of times. It's also effective.
I'd imagine with
so
your
I was gonna say a lot of the, I mean, so we're alluding to the fact that a lot of these polymers are formulations themselves, right? So what are the ingredients you use to make the polymer depends on where you want to stick it. And usually you're going to put in something to stick to one side and also something to stick to the other side while trying to get the right rheology so that the peel value is high enough. So that's part of the fun.
Yeah, and in the formulation field, I think we have like several tools to make those interactions more effective and can happen, right? That's why the formulation is not only the polymer and one more ingredient. It's like a different kind, like it's like a lot of the ingredients that go into one formulation to give us the exact properties, to give you like the strength that you need for the bond to make sure that it will bond to the different substrates. So it's not an easy recipe.
All right. Now, here's another big question. What is the difference between a glue stick, liquid glue, and the kind of glue you can make at home?
What's the kind of glue you can make at home?
I think they're referring to the one with milk that's in our Celebrating Chemistry magazine, actually.
Oh, okay. I haven't done that experiment. Okay. What's the difference? So I can tell you about a glue stick first, and I'll move on to the other one. So the glue sticks are hot melts, and they're very simple formulas. They're two things normally, or two things, or sometimes one thing. They're polymer and tackifier, usually EVA and rosin ester, or if they're one thing, they're polyamide. And they're quite simple. They're not going to have great resistance to any kind of to some chemicals anyway, and they're not going to have obviously high temperature resistance because they're hot melts, right? They melt and they never cure. And what was the other one? Yeah, liquid glue. liquid glue. I think you're talking Gorilla Glue.
Or Elmer's or anything like that, I think.
Those are very
Oh.
different.
Yeah. I thought you were talking super glue.
Not say
So there's a
super
lot of liquid glues
could
is
be
the
asked.
answer. And they're all very different, right?
Yeah, that's true. So
yeah,
super
they're all-
glue are cyanoacrylates, the chemistry.
If you go to your hardware store, you'll see cyanoacrylates, right, which are basic cured. The base is moisture. You'll see polyurethane prepolymers, which are moisture cured as part of the reaction, not the initiator. That's what Gorilla Glue is. And then you'll see these emulsions, which are just, you're breaking the emulsion. Mostly they're vinyl acetate based with a little bit of crosslinker in there. And those systems will, they just dry out and they stick. And that's probably what your milk experiment is, except it's an emulsion of proteins, natural proteins that are there. So
Yeah, so a lot of
add anything to that?
A lot of chemistry goes into adhesives and glues. I think you're hearing that from Chuck's description, and yeah, that's why we have jobs, is that it's there is a lot of complexity out there, and a lot of chemistry that goes into it, for sure.
That's great. Well, I think we have time for one more question. What are the most exciting future directions for the field?
Well, I was thinking about that one too. I think probably space, probably like continue to develop adhesives that will survive, like in rockets, but also, like thinking of colonizing other planets. I think the environment that we will like face out there will be like very, very different to what we are now facing on Earth, right? So I think that's a very long shot, but it's definitely like, I like to think about that, like that future. And I know that there are a lot of companies working towards that, right? Like basically going to like Mars or other planets, right? So I think we need to probably like start thinking about that, like development of new materials for these type of applications take a long time, and there will be like a lot of things to consider. So I think, I think space would be like one field that will be very important in the future. I think it's getting a lot of importance like now. So learning from like all the developments that we have right now for aerospace and basically leveraging that knowledge to like take it to the next level will be very important. The other field that I think continues to be important is the medical field as well, like I mentioned before. Yeah, I think those two will be probably like the most exciting, together with adding the sustainability to the whole package, right? Like developing these new adhesives for this new environment, for example, for like space or like medical fields, but make them more sustainable, right? And in the medical field, that will be also that will help us to make the adhesives easier to be accepted inside the human body. Yeah, that's my take on that.
Anne, would you like to add something?
Oh, sure. Sure. So, yes. So, and we've hit on it before, and Alejandra said it, but sustainability, I think, is really important. And, at 3M, we think about sustainability in sort of three ways. Science for circular. So we talked about that a little bit around recyclability and raw materials. Science for climate. And so we talked about that as well. How do we in our processes take material out so we're not having so much scrap material? And then science for community. And this is by no means an adhesive only statement, but I think that, in STEM, the the more open we are, and the more inclusive we are and looking for diversity, the better off we will be. So there are these important issues, like Alejandro was saying, so sustainability, space, medical applications. We need the brightest minds, and it's important that we're not just drawing from one subset of the scientific community or of the community. So I'm really excited about diversity and inclusion, and that's part of this, certainly, again, not just for adhesives. But yeah, so that's I think those are the areas that I would say I think are exciting for the future.
Yeah, and on the adhesion science side, to me, I think when we touched on it already, the connection to genetically engineered microbes. So one really exciting one I wanted to mention that we're looking at now, and we haven't done it. This is external. Is self-healing cement, where this is a really cool example. There, you're seeing people putting microbes into nonwovens to eat all the food that the bacteria that would have gone there to make your sneakers stinky. In this case, cement, they're putting it into the cement, a dormant encapsulated microbe that if water gets in, they get released, and they eat some of the calcium oxide and convert it back to limestone, calcium carbonate, and seal the crack. So you've got microbes sitting in your cement waiting to heal the cracks for you. I just think that's so cool. But biology, I think that's the place really going forward.
Great. Well, I'd like to thank you all again for your time today, and I'll pass it over to David to close us out.
Awesome. Thank you, Lily. And thanks to all of our panelists for joining us today. We want to thank everybody in the audience. We want to thank our partners at 3M, Henkel, and Facebook for their efforts preparing us for this event. And lastly, a big thanks to the Adhesion Society for being such a great collaborator this National Chemistry Week. They helped us a lot with content and subject matter experts, and we hope all these really exciting future directions come true. I'm pretty excited about it. So after we sign off today, I encourage you to take to social media feeds and post about what you've learned. Make sure to use the hashtags, hashtag National Chemistry Week, hashtag NCW, hashtag Sticky Chemistry, and hashtag Chemistry. Also, follow the American Chemical Society on Facebook, Twitter, Instagram, and LinkedIn to see all of our campaign coverage and for other chemistry-related news, awards, programs, and other offerings. Let's see. And if you have any questions, please contact us at outreach@acs.org. We hope to see you this spring as we host Chemists Celebrate Earth Week, our annual Earth Day celebration from April 18th to the 24th. And you can find more information at www.acs.org/outreach. So goodbye, everyone. Happy National Chemistry Week again, and thank you for celebrating chemistry with us.
Bye-bye. Thanks.
Thank you.
But thank you.
Bye.